Hello, everybody. Thank you for tuning in. My name is Leo Dirac, and I'm a principal engineer on the Amazon SageMaker team, and I'm going to be talking about our new automatic model tuning feature. So to start out with, we're going to talk about what hyperparameters are and how you tune them with the automatic model tuner and why it's important to tune hyperparameters in the first place. Then we're going to dive into an actual demo using a Jupyter Notebook instance in SageMaker to perform some model tuning on a real-world data set and using a real problem. And then we will talk about some tips for how to effectively use the model tuner. So to start out with is some background. Let's talk about what is a hyperparameter in the first place and why do these things even need tuning. So what we're dealing with here is supervised machine learning. So this is the classic problem where you are trying to learn some function f that takes a vector of data x and maps it into some value y. And what we're doing is, given some value of x, we're trying to predict a value of y. And we do this by feeding a machine learning algorithm a bunch of training data. And these are pairs of x, y, where given some x, we know the correct answer for y. And we feed these over and over again into an algorithm until the algorithm learns a good generalization. It finds patterns in the x's that helps it make good predictions for y. So this is standard machine learning stuff, right? But something that you might not realize is that everybody here is capable of building a perfect machine learning model every time. And I'm going to show you the algorithm for doing this, one that can predict the correct values on the training data every time. So what you do is you start out with a blank model, which is just an empty dictionary, and it gets fed many batches of data, the x and y, and it goes through them one at a time, pulls out the pairs of x, y, and then it records the value of y for any given x into this dictionary. And now it's got everything stored, so when it comes time to make a prediction, all you have to do is look up that value of x in the model, and you return the value of y associated with it. And if that value of x isn't in the model, then, well, you're really just out of luck. And this is the problem with this algorithm. Although it is perfect on the training data, it has absolutely no capability of generalizing to data that it hasn't seen before. So it's actually not useful at all. But it illustrates a fundamental problem of machine learning, which is overfitting. So to visualize overfitting, consider this example, where here we have, say, two axes of the original data, and the red and blue points represent different scenarios. For example, red could be customers that are likely to continue with your service, and blue are customers who are likely to churn out of your service. So this could be a classic churn prediction model where you're trying to figure out who to spend more attention on in your customer base. And the green line here represents a model which exactly fits the training data. Just like that perfect algorithm that I showed you before, the green line has memorized the data set and exactly separates the blue and the red data. And as you can see intuitively in this diagram, it's probably not the best model for the situation. In fact, the black line represents what is likely to be a better model because the green line, although it's perfect on the training data, it's unlikely to generalize well to unseen data. So the way we get from the green line to the black line is generally a process called regularization. So regularization is something that you can do to a machine learning algorithm to simplify the model and force it to not be quite so careful in capturing the subtleties of the training data that maybe don't represent real patterns but are just kind of anomalies in the data. So regularization is a way to kind of force the model to be simpler and avoid just memorizing the training data like we did in our so-called perfect algorithm earlier. And the way you know how much to regularize it, how simple to force your model to be, is to hold out a test set from your training data, and then you measure how well the algorithm or the model performs on this held out test set. And so that's how you know how much to regularize the data. So regularization is a classic example of a hyperparameter which you need to set based on your data set and your particular problem at hand in order to get the best performance out of your machine learning model. Now, if you have a lot of data and a sophisticated algorithm, then it's going to be able to find very subtle patterns in the data set and thus create a very sophisticated expressive model. And you might not need very much regularization. But if your data set is relatively small, you're likely to need more regularization in order to avoid overfitting the data set that you have. And thus, regularization is an example of a hyperparameter which you need to set in order to get good results on your machine learning problem. Another example of a hyperparameter is learning rate. So typically, modern machine learning algorithms learn their models iteratively. And so what they do is they observe the difference between the prediction from the current version of the model and the correct answer in the training data. And they take the difference, use that to calculate a gradient, and then update the model by a small amount in order to make the trained model be somewhat closer to the training data and thus give better predictions the next time around. Now, what do we mean by a small amount? So from calculus, we know that we can approximate any curve as a finite series of steps. And that's what's going on here. You're taking this smooth surface of the loss surface in your machine learning model and approximating it with small steps to get to the bottom of this loss surface. But how small of a step do you need to take? Well, from calculus, you'll remember the smaller the better. The smaller will approximate the curve more closely, but if you take very, very small steps, then it's going to take an extremely long time for your machine learning model to converge. So there's a trade-off here generally, and this is, again, one of these hyperparameters that you need to pick a value for to say how small of a step you're going to use when you're updating your model. And the size of the step that you need to take, you just don't know ahead of time. You don't know until you've started working with your data set what a good learning rate is going to be. Just like you don't know how much you need to regularize your model in order to get good generalization performance on unseen data. So I'm going to offer this definition of a hyperparameter for you. A hyperparameter is any decision that the original author of the algorithm can't make for you, and it needs to be decided based on your specific problem and your specific data set. And as such, hyperparameters are necessarily things that you need to pick. You as the practitioner, you the person who is using this algorithm to come up with a model on your own data set, need to pick values of these hyperparameters like the learning rate or like the regularization. Now, for modern machine learning algorithms like deep learning neural networks or boosted trees or random forests, the expressiveness of the model is something that is configurable through hyperparameters. In the bad old days of machine learning, if you wanted to get a more expressive model that was more sophisticated and able to capture more subtle patterns in your data, you had to switch to a completely different algorithm, a different set of math, a different set of code. And this is very clumsy. But nowadays, you can use one algorithm like a neural network, and you can change how expressive that model is simply by changing hyperparameters like how many layers in the neural network. If your model seems to be underfitting, if it's not capturing the subtleties in the data, you can try just adding another layer to the neural network or increasing the width of each of the layers you have by adding more hidden nodes. And this is doing kind of the opposite of regularization in that these are ways of making the model more complex and more expressive. And so the expressiveness, as expressed through these hyperparameters, is in direct conflict and tension with the regularization hyperparameters. And here, again, is another reason why you need to tune these hyperparameters. Nobody can tell you whether you should use a small neural network that's lightly regularized or a very large neural network that's heavily regularized, because it's going to depend on the specific problem that you're working on. And there's analogies in tree-based systems as well. So we've talked about a couple different types of hyperparameters. There's ones that control the expressiveness of the algorithm and how complex of a model you can learn. And then there are regularizing hyperparameters that force a model to be simple and avoid overfitting given the amount of expressiveness that you have. Also, very often there are optimization hyperparameters like the learning rate, which control how the algorithm learns the model given the data set. So learning rate's one example, but if you're using a momentum-based optimizer, then momentum is another hyperparameter. If you're using ATOM or RMS prop, there's even more hyperparameters. When you talk about changing the learning rate over time through the learning process, that learning rate schedule also exposes hyperparameters related to the optimization that you need to choose in order to get the best results for your model. Additionally, when you're handling the data, the processing that you do often exposes choices that need to be made as well. For example, if you're doing text processing, you might want to create bigrams or trigrams or 4 grams or 5 grams or 6 grams. And the number of grams that you choose is one of these arbitrary choices, which is hard to know ahead of time and varies based on the data set and the problem. And similarly, or generally, any kind of feature processing that you do on your data set is likely to expose some hyperparameters which might need tuning, where the value of this hyperparameter, which affects how the processing is done, is going to change the final results of your model and affect the quality of it. And finally, the last kind of hyperparameter I'll talk about generally, I'll call algorithmic. And what I mean by this is that it's possible to completely switch algorithms using a hyperparameter. You can expose a hyperparameter, and a lot of systems do expose hyperparameters which are just Boolean flags, and these correspond in the code to if tests. And they say if the hyperparameter is set to this, run one block of code, and if it's set to false, then go run a completely different block of code. And this is often what happens when the algorithm author isn't sure which of two approaches or many approaches is best suited for every problem. And so they'll just leave these as choices. So if you look at a complex, mature package like XGBoost or Sockeye behind the SageMaker's sequence-to-sequence package, they expose a very large number of choices which just switch how the code functions. And so these algorithmic hyperparameters can have a very large impact on how the model behaves because they can run completely different algorithms based on the hyperparameter that's chosen. Okay, so now I think you've gotten a sense for what hyperparameters are and the fact that they need to be tuned and chosen appropriately for your problem at hand. So let's talk about different strategies for doing this tuning, for how to pick the best hyperparameters for your algorithm and data set. So the classic basic strategy is simply just trial and error. In academia, sometimes this is referred to as GSD, or graduate student descent, where somebody just picks a set of hyperparameters kind of from intuition and best guess. They train the model, and they see how good it is based on the held-out test data. And then they scratch their heads and think about it and try turning a couple knobs and dials and doing something a little different, and then they try again. And they repeat this process over and over again until they're out of energy or they reach their deadline. And so this is common, and this is where most people start. When I started training deep neural networks 5.5 years ago, I looked at all these things and I thought, wow, there's got to be a better way. And so some people will jump to the conclusion that why can't we just try everything and use what works best. Try all the possible hyperparameters and just use the one that gives us the best results. And that intuition is actually smack on. That's exactly the right idea. The problem with it is just in the practicalities. Now, hyperparameters like learning rate can be any positive value. So you can't actually try every possible positive number as your learning rate. So the realistic way to come close to this that people will typically use first is called grid search, where you say, I'm just going to try a certain number of values for each of the hyperparameters I'm interested in. So to visualize grid search, consider that you're tuning two common hyperparameters, learning rate and regularization, and you've decided on some range of reasonable values, and you say, I'm going to pick 5 values inside each of these ranges and try all the combinations of those. So in this case, we have 25 combinations of hyperparameter configurations that we're going to try. And then we run all of them. We run a separate machine learning we build a separate model for each of these, and we pick the one that gives us the best results on the held out test data set. And this is a fine approach, but it has some limitations. And especially when you start dealing with more than just a small number of hyperparameters. So consider this geometric analogy, and let's say you're tuning only 2 hyperparameters like learning rate and regularization. And all you want to do is try the corners of this configuration space. That's 4 training jobs. Now, if you want to try the corners and the middle on each axis, you're up to 9. If you want some variation, you're up to 25. And if you want to try actually a reasonable range, you're already up to running 100 training jobs just for these 2 hyperparameters. Now, let's say you add a 3rd hyperparameter, like the depth of the network. Now, to get a reasonable range, we're up to 1,000 hyperparameters. If we add another hyperparameter, like the width of the network, we could jump up to 10,000 to get a reasonable range. And it's easy to come up with 5 or more hyperparameters that you might want to tune. And you can see that the space of configurations that you might want to try explodes exponentially based on the number of different hyperparameters you want to tune and how fine-grained you want to be in searching each of these possible hyperparameters you're tuning. And this is one example of a common problem in machine learning called the curse of dimensionality, which very generally means that when you're dealing with large spaces, high-dimensional spaces, they are extremely big. It's really hard to wrap your head around intuitively how big a 5-dimensional space is, much less a 50-dimensional space or a 1,000-dimensional space. These spaces are incredibly huge, and you can see just from this simple example that even when you're dealing in just 5 dimensions, that the number of possible points you'd have to use in order to cover that space with any degree of coverage is extremely large. So while grid search intuitively is a sensible strategy, and it can work for small problems, it turns out that random search is much better, which is to say just picking points randomly in the configuration space tends to outperform grid search. And I tell you this empirically, which means that's just kind of how it works in the real world. And the intuition for this is given from a classic paper by Bergstra and Bengio in 2012 on random search for hyperparameter optimization. Now, imagine again, we're just tuning 2 hyperparameters, and here they're only choosing 3 points along each axis. And let's say that one of these hyperparameters is very important and has a very high impact on the quality of the model, and one of them is really not all that important. And this actually happens all the time. This is very common because these mature algorithms expose a large number of hyperparameters. You can't or shouldn't tune all of them, and so you need to pick which ones you're going to tune, and so you do that based on your intuition about which ones are the most useful. And one of them you might get right. You might pick one that's extremely important, but you also are likely to pick one or more that just aren't all that important. And as the visualization on the left shows, if you do this, then the important hyperparameter gets repeated over and over again with variations on the unimportant hyperparameter. So even though we've trained 9 models, we've only picked 3 unique values for that important hyperparameter. Whereas on the right, when you pick your configurations completely randomly, then it's extremely unlikely that you will pick the exact same value more than once for the important hyperparameters. So you end up sampling 9 unique points of the important hyperparameter, and you're much more likely to find a good configuration and get good results quickly. So it turns out that grid search is just inefficient, and if you don't have access to a high-quality tool like the automatic model tuner in SageMaker, random search is really a great way to go. It's incredibly simple to implement. It parallelizes embarrassingly easily. The workers don't need to communicate or share any state whatsoever. They just pick a new random configuration and go with it. And it's actually a great baseline for any kind of hyperparameter tuning, is to just pick points randomly. So random search is actually a fine tuning strategy. But we're going to do even better than that. We're going to try using machine learning to improve our machine learning. And the way we're going to do that is called Bayesian optimization. So now let's dive into the technical details of how the automatic model tuner in SageMaker works. What is Bayesian optimization, And how is it that we're using a machine learning meta process to improve the quality of our machine learning models that we're building in SageMaker? We do this with what's called a surrogate model. And a surrogate model is, in some sense, just a classic, simple supervised learning model where we're trying to predict y given some x. But in this case, x is the hyperparameter configuration that controls the algorithm on the model that we're building, and y is the quality of the model. So this could be the accuracy or the root mean squared error of a regression problem. But this surrogate model, what its job is given a hyperparameter configuration, some vector that describes the machine learning process, it tries to predict the quality of the model that will ultimately be produced. And the idea is that this surrogate model can be evaluated much, much more cheaply than actually training a real machine learning model on your actual data set. It could take hours or days to train a real machine learning model, but evaluating the surrogate model can be done in seconds or minutes. Now, one thing to note about this surrogate model is that there's no gradient information available. It's impossible to differentiate through your Docker container, through your code in SageMaker, in order to get a gradient on how you should change the hyperparameters in order to improve that model quality. Now, in some cases, it is actually possible to get a hypergradient in hyperparameter optimization, but that doesn't work generally in a platform like SageMaker. So we need to use a kind of machine learning model which is based on gradient-free optimization. And what we're going to use, and what we use in SageMaker for the surrogate model, is called a Gaussian process. And Gaussian processes are great because not only do they predict y as a value, but they predict y as an uncertainty range. You get a middle and a variance, a mean and a standard deviation for every y that comes out. So to visualize what this looks like, let's pretend we're tuning just a single hyperparameter on the horizontal axis, and the vertical axis is the quality of the model that comes out. And the vertical axis is error, so we're trying to find the lowest value possible. So in this case, we're looking for these bottom points on the red curve, because the red curve represents the truth, the actual quality that the machine learning algorithm is going to produce on our data set. So we're looking for these bottom points. And so far, we have trained 2 models to inform the surrogate model. We've trained a model here, and we've also trained a model over here. And so the red line represents the actual function that we're trying to approximate with the surrogate model, and the black line is the surrogate model itself. It's the black line is the mean, and these gray bands are the variance, the uncertainty that the surrogate model has. And so you can see that on the points where we've actually trained a model, the uncertainty is 0. The surrogate model knows exactly what the right answer should be in both of these positions. But when you move away from that, the surrogate model is really unsure what the right value should be. So it has very high uncertainty. So now, based on the surrogate model, we're going to pick the next hyperparameter configuration, which is just a single value in this case, to train the next model on. And we're going to use this using an acquisition function, which is just some way of valuing all of the possible configurations. And the particular acquisition function that we're going to use is called expected improvement, or EI. And EI is, it's looking for the lowest possible value in this uncertainty band. And you see it comes pretty low over here, but it's actually lowest over here because intuitively we just know very little about what's going on in the left side of this configuration space. So the surrogate model says that we should pick this blue dot as our next hyperparameter configuration and train a model based on it. So we do that, and the value that we get is right on that red curve, and the surrogate model's uncertainty collapses at that point, and it updates itself, and it gets a new shape based on this new piece of information that we have, which is this third data point, this third set of training data for the surrogate model. And now, if you look at the acquisition function down here, we see that there's 0 value in repeating the exact same configurations that we've done before. And over here, there's 0 value even around it, because this one is worse than the other two that we've seen. And we know, based on the surrogate model, that we're just not going to get a good result anywhere near, well, very nearby this model that this configuration that we've already tried. So it says the best thing to try is this blue dot here. So we train a model there, we update the surrogate model, and now the best model, it thinks the best value is likely somewhere around here where we haven't tried anything. That one also turns out to be not very good because of the shape of this, the shape of the red curve itself. But you can see that through a series of successive approximation, the surrogate model gets updated to be a pretty close approximation of the actual red line, and we find the configuration that gives us pretty close to the best possible results on this data set with this algorithm. So that is an intuitive explanation of how Bayesian optimization works, which underlies the automatic model tuner in SageMaker. Now, let's dive in and go hands-on to actually trying this thing out. And what we're going to do is we're going to work on a forecasting problem using the DeepAR algorithm, which is built into SageMaker. Now, forecasting is an interesting problem because it applies to a very large number of real-world business problems. If you can predict the future, then clearly this is going to be useful for a lot of things. DeepAR is interesting in this case because it exposes a lot of hyperparameters, a lot of things to tune, and because DeepAR is a deep neural network, tuning is very important. These neural networks are very expressive and very configurable. You can change them from incredibly large, capable of capturing vast amounts of information and very subtle complexities in your data, or they can be tuned down to be very small and very simple, which is appropriate when you have a relatively small data set, but it can't capture a lot of subtlety. So you'll see with DeepAR that the results you get vary wildly based on how you tune it. So tuning is very important. Okay, let's jump over to the notebook. Okay, so here I am in SageMaker, and I'm looking at my list of notebook instances, and I have a notebook instance running already called the Model Tuner. And so I am going to open up this notebook, and here I am inside of Jupyter. So Jupyter IPython interactive development environment is great. And what I did is I went into the SageMaker examples, and I went into Introduction to Amazon Algorithms, and here is the DeepAR electricity example. And this is the example that I have based this on, and this shows you how to train DeepAR on a real-world data set of electricity usage. Now I've taken this and I've modified it to be able to actually tune the hyperparameters instead of just running a single training job. And let's walk through this notebook and use it to actually launch a tuning job. So the notebook starts out just importing a bunch of libraries and setting the random seed so that the results are somewhat reproducible, setting up a session object, and then getting access to S3 and an IAM role with permissions to access S3. We create some paths, we look up the Docker image for DeepAR, and now we find the data set in the UCI machine learning data repository. And we go and we download it. Now, this is a fairly large file, so I've actually already downloaded it onto this notebook instance. It can take a while if you haven't, or the first time you do this. Now, we load the data set from disk into memory, and once we've done that, we can visualize it. Now, DeepAR is good at forecasting a large number of time series simultaneously. What it does is it looks at each time series and it uses that to inform the other time series that it's working on. So these are different amounts of electricity being used by different customers. And you see some of them are very periodic, some of them are less so. And so this is just showing you what the data set looks like. Now we split it up into train and test. We use a week of predictions for each of them, for the prediction length and the context length. And doing this properly for forecasting is a little bit tricky, so I should dive into the detailed notes here in the documentation to understand that if you're actually working on a forecasting problem. But we divide up the data into training and test, and we see that we have 1,500 points in our test set. We write these out to files, and now we upload them up to S3. And once they're up in S3, we download a little bit just to check to make sure it's all there. And now we are ready to train our model. So we create this estimator object in SageMaker. We pass it the session, the name of the Docker image, the access role. We pick the cluster that we're going to run this on. So we're going to use a single ML C4 2x large machine. And we point it to the output and where the training data and test data are. Now, here's where I started changing it. Everything there is exactly the same from the original example, but here is where we set the hyperparameters. And I've renamed these to static hyperparameters because these are the hyperparameters we're not tuning. And so things like the time frequency and how the week of prediction and context length and the number of epochs, we're all going to leave all those fixed. And the learning rate was set originally, but I've commented this out because I want to try tuning the learning rate. So we set these static hyperparameters into the estimator, and now we import the libraries from the SageMaker tuner in order to set up the tuned hyperparameter ranges. And so we're going to try tuning the number of cells in the neural network and the number of layers. So these are expressiveness. The more layers and the more cells, the more expressive the neural network is. We're also going to tune the dropout. And this is a regularizer in neural networks. It's very powerful. And I'm going to try tuning it up to a very high range, up to 0.9, which is beyond what they recommend in the documentation. But I've seen neural networks behave pretty well when they're set to be very expressive, but are heavily regularized. Embedding dimension is another way to adjust expressiveness, and here's our learning rate. So I've chosen a reasonable range of 10 to the minus fifth to 10 to the minus 1, which seems like a reasonable range for learning rates to be tried upon. So you can see some of these are integers, some of these are continuous. We don't have any categorical hyperparameters in this choice, and categorical would be if you have a fixed set of choices, like if you're choosing between A or B, SGD or Atom, for example. We set those up, and now we create the hyperparameter tuner object. We pass in the estimator, which has the algorithm information. We need to pick the objective metric, and this is a critical concept. The surrogate model needs to know the Y values. It needs to know what it's optimizing for. And so to do this, we pick the metric which is being emitted from DeepAR that we're interested in optimizing. So in this case, we're optimizing for the RMSE, which is the root mean squared error, on the test set. And we need to minimize this because we want the error to be as low as possible. We pass in the tuned hyperparameter ranges, and now we need to say how big our budget is and how to control the tuning process. So what we're saying is we're going to run up to 50 jobs total, 50 training jobs, and we're going to do 10 of them at a time. And once we have all this configured, we give the job a name, tune elec, and then some random string, and we hit go. And now it has created the hyperparameter tuning job with the name tuneelec 9AFA9. So we pop on over to our SageMaker console again, and we come down here under training to hyperparameter tuning jobs, and we see that there are two of them. There's this one that we just launched, and there's another one that I ran before this. So the one that we just launched, we can go and we can look at the hyperparameter configuration, and this is everything that we set up. So you can see the embedding dimension goes from 10 to 100, the learning rate goes from 10 to the minus 5 to 0.1. These fixed values, these static values like the prediction length and the time frequency are passed in, and there's a list of training jobs. And you can see there's 10 training jobs all in progress, and none of them have completed to give us the objective value that we're interested in. Now, this is going to take probably a few hours, so rather than make y'all wait, I already completed one of these with the exact same configuration, and here are the results. It took 15 hours to finish all of this. Sorry, so that's 15 hours of machine time. And we can see that each of these 50 jobs has a different value for the objective metric. This one did amazingly badly, up at 100,000. Some of them are in thousands, some down in the hundreds. But let's sort by the objective metric to see the best value. And the best value it found was 402, the lowest error. we jump over here to look at the best training job. And the one that you probably care about, the one with the best value on the objective metric, is always highlighted for you right here. And you can see that over all of these models that it tried, the one that gave the best results had a moderate learning rate. It didn't go to that extreme dropout value that I let it try. It had a pretty large number of cells, a moderate number of layers, and in all the things it tried, this is what gave a good configuration. Now, if you want to use this model, you can just hit the Create Model button, and you will be ready to host this model in a prediction setting and be able to get live inference out of it. So creating a hyperparameter tuning job is a small modification on the API call from creating the training job. All you need to do really is to specify the ranges over which you want to search, for which hyperparameters you're going to pick, tell it how you define success, what is your objective metric, and then how long you're going to search for. And then other than that, it just works like training a single machine learning model, but it's going to try a whole bunch of them and figure out what's working best within the constraints that you specify. Okay, now back to the presentation. Now that we've seen how to use the automatic model tuner, I'm going to give you some tips for how to use it effectively and how to get the best results out of it. So when you're thinking about using the model tuner, it's important to be clear on what you're trying to accomplish. So the most straightforward goal is to just get the highest quality model you can out of your data set on the algorithm that you've chosen. And often this is exactly what you want, and this is what the model tuner is designed to do. So if that's your primary goal, great. But sometimes you also want to understand what's going on inside of your model. You want to understand your data set and how the algorithm is interacting with it and what those hyperparameters actually mean. And if this is part of your goal, you should be clear about that, because this is somewhat in tension with just getting the highest quality model that you can. And another thing to clarify is, are you interested in getting your results as quickly as possible, or are you interested in optimizing for using the fewest possible resources? Because there is a quality time trade-off in setting up the hyperparameter tuning job. And it's really embodied in that one number that we specified, which is the maximum number of parallel jobs. So we picked 10, right? We said run 10 jobs at once. But you can also say just run a single training job at a time by setting max parallel jobs equal to 1. Or you can set it as high as 10, and then it will run 10 clusters of jobs, 10 clusters of training jobs all at the same time, and search through configuration space in parallel. Now, the reason you would pick 1 is because it's going to result in the best surrogate model. By doing the training job serially, the surrogate model has access to all of the information it possibly could, all of the training data, to update itself and get the highest quality surrogate model at any given time. Whereas if you are running lots of jobs in parallel, when one job finishes, we don't wait for the other 9 to finish before updating the surrogate model. We update that surrogate model right away and get another job launched as soon as we can so that we can get you the results as quickly as possible. And so you would expect, and it's often true, that if you set the parallelism really high, that the surrogate model isn't going to have access to as much information, and the quality of the final model is not going to be as good as if you run them in serial one at a time. But it turns out that by running them highly parallel, you often end up with similar final model quality as if you do them one at a time. And I'm going to quantify this for one particular example for you. Now, running them one at a time obviously requires the longest amount of clock time, whereas if you do them in parallel, the results come back much faster, almost literally 10 times faster. But the key trade-off is that by taking a longer amount of time, the surrogate model has more information, and you're likely to end up with the best possible model. Now, I actually measured this on the DeepAR electricity example, and here are the results that I found. So what I did is I ran a whole lot of tuning jobs, and I configured these hyperparameter tuning jobs at different sets of parallelism. So the red line was doing serially 1 at a time, and the blue line was doing it as fast as possible 10 at a time. And in between, there's 2 at a time and 5 at a time in the yellow and green lines. And I ran 5 tuning jobs at each of these configurations. And what's plotted here is the mean and standard deviation of the results, which is the best validation error we'd seen after each number of training jobs. And we see that the best validation error starts fairly high and then quickly drops down, or steadily drops down in each case, and results in a reasonably good model. And in this set of experiments, the 2x got lucky, and it seemed to have found pretty good models very quickly, in fact, better than any of the others. But they all decreased down, and if you look at the standard deviation and the variance between them, it's not clear to me that there's any statistical difference between the results. They're all about in the same range and the same variance. This is one look at it. If we change the x-axis to, instead of being number of jobs, if we look at it in terms of elapsed time, wall clock time, we see a very different picture. All right, we see that, again, they're all converging down to about the same result. Again, yellow looks a little better, and for some reason, red, which is the 1x, didn't do super well this time, just got unlucky. And I think that's because the DeepAR model has pretty high variance. These neural networks have a high degree of variance in them because they're very expressive. And but if you look at the x-axis, the difference is stark, right? When running it with a parallel factor of 10, it took less than an hour to complete all of those jobs, whereas when running them one at a time, it took over 6 hours to get the result. So in this case, we didn't actually see that trade-off at all between quality and time. The higher parallel was just better. But in some cases, I've done lots of these plots, in some cases there is a noticeable difference between the quality of the final model when you run the results serially versus in parallel. Okay, so that's one thing to consider when you're using the automatic model tuner. Now, if you're interested in gaining intuition about how the hyperparameters work and understanding your model, there is a sample notebook available in all of these SageMaker notebook instances called HPO Analyze Tuning Job Result. And this will help you visualize the results of all of the machine learning models that were created, because you have access to all of them. They're all there in your SageMaker console. Every one of these 50, or you can do up to 500 of these training jobs are there, and you can see what hyperparameter combinations were chosen and what the results were for each of those configurations. So you can visualize these to start to understand what the shape of the configuration space is in terms of the quality of the model that you get. And if you're interested in gaining intuition here, my strong advice for you is that fewer hyperparameters tuned are going to give you better intuition. In fact, if you really want to understand a hyperparameter, just tune it by itself. Just pick one hyperparameter, specify a range, and run 10 or 50 jobs in that range, and you will see a nice curve showing you exactly how the model quality varies on that one hyperparameter. If you want to do things a little more efficiently, you can do 2, and then you can draw a heat map and look at the relationship. And the notebook here, the sample notebook, shows you how to do this. It'll actually do the one-way correlation plots for you and puts everything into a pandas data frame so you can visualize it however you want. But once you have more than 2 hyperparameters that you're tuned, your configuration space is starting to get big. If you have a 3 or a 4-dimensional configuration space, then trying to understand that is really challenging just from a visualization perspective. So again, my strong advice is if you want to understand what's going on here, you should tune fewer hyperparameters at a time. And this is in contrast to getting you great results at the beginning. But to really understand things is the path to getting truly great results. So some more tips. Avoid categorical hyperparameters if you can. So for example, let's say you're tuning dropout and you think to yourself, well, maybe I want 0, or somebody said 0.2 and 0.5 seems pretty common, so I'll just try those 3 options as a categorical parameter. So categorical means picking amongst a fixed set. And you can choose a fixed set of values for a continuous hyperparameter like dropout or an integer parameter, but it's not advised. If you have something that is numeric, treat it as numeric. Because if you treat it as a categorical, then the surrogate model doesn't understand the relationship between these. And if you say the dropout might be 0 or 0.2 or 0.5 or 0.7, then each of those, as far as the surrogate model is concerned, are completely unique snowflakes and have no relationship to each other. So you're making the surrogate model's job much harder by using categorical parameters. And if you can use continuous or integer parameters, you should. Another piece of advice is to keep the search ranges reasonable. And what I mean by that is consider learning rate. Learning rate can be any positive number, right? But don't set a range of 10 to the minus 99 to 10 to the plus 99, or even 10 to the minus 10 to 10 to the plus 10. Include only in the search range values that you think might reasonably create a good model. Because if you create your configuration space to be too big, the search space to be too big, again, you're making the surrogate model's job very difficult. The surrogate model starts knowing nothing about your problem. And so the first few models that it tries are just completely randomly guessing. And if you've created this massive configuration space, which is mostly filled with these values that are completely unreasonable, then it's going to have a very hard time finding anything that gives good results to get any traction on honing in on a good result. So try to keep things reasonable. Don't make them too small. But you will see that, say you set the range between, say, 0.001 and 0.01 on your search space, and all of the high-quality results seem to be centered around one of the edges, that's going to imply that the range is too small and you need to expand it. If you see the tuner focusing its energy on one side of one of your ranges, that means your range is probably too small. And one more piece of advice, don't tune everything that's tunable. Something like XGBoost exposes over 40 hyperparameters. It's not even possible to tune all of them. But again, think about the cursive dimensionality in the size of the configuration space. Just because something is tunable doesn't mean you should. Pick the ones that you think are most likely to give you the good results. And if you're not sure, the documentation for the built-in algorithms has advice on what is most likely to give good results. And finally, I'll say that the automatic model tuner it's not magic, but it is a wonderful tool that can increase your productivity. It can help you explore lots of possibilities very quickly using the power of the cloud. And if you're developing your own code for your own algorithm, then it can help you gain confidence very quickly that your approach is either working or not. You can use the model tuner to rule out an approach by trying lots of different variations on it and say, well, none of these are working, I need to try something else. Or you can try searching over a set of configurations and gain confidence that the model that you found is the best possible within that space. So it's a great productivity tool, but it can't work magic. You need to be thinking about what it's doing in order to use it effectively. And at that, I will thank you for your time, and I will gladly take any questions that you have.